Hello and welcome to the next lecture. Today we're going to talk about moments, Laplace transforms of derivatives, and solving initial value problems with the help of the Laplace transform. We begin with moments. A moment is a multiplication of f of t by t to some power. You may remember it from calculus. When you were finding moments, you were multiplying f of t by t and integrating. There's also similar definitions, probability theory. So what happens when we multiply f of t by t, and what happens to its Laplace transform? As usual, we're going to assume that f of t possesses a Laplace transform, and so when we take a Laplace transform of t to some power f of t, the result is the derivative of the Laplace transform with -1 to the power n in front of it. So if we just multiply by t, it's going to be negative the derivative of f of s. If we multiply by t squared, it's going to be plus positive second derivative of f of s. The proof of this theorem is interesting because the proof approaches the problem completely backwards. So instead of taking the Laplace transform of t to the power n f of t, let's do it differently. We're going to take a derivative of f of s. Well, that means we're taking a derivative of the Laplace transform integral. Well, integrals allow us to perform the integration inside of it, so we can switch the order of integration and differentiation in this case. So that's going to be the integral of a derivative well, the only thing that depends on s is the exponential function, and its derivative is simply minus s minus t e to the minus st. Remember, we're taking a derivative with respect to s. So this ends up minus the integral of t f of t times e to the minus st. And that's exactly the Laplace transform of t f of t. So as a result, we can say that the Laplace transform of t f of t is minus the derivative of f of s. Well, what about multiplying by t to the power n? Well, what if I do the Laplace transform of t squared f of t? Well, that's going to be the same as the Laplace transform of t times t f of t. So that's going to be minus the derivative of the Laplace transform of t of f of t, which in its own right is minus the derivative of the Laplace transform of f. Extending this to the power n, we get the Laplace transform of t to the n, Well, if we repeat it n times, we're going to get minus 1 repeated n times, and the process of differentiation performed n times. And that's the proof of the theorem. And let's take a look how it plays out in examples. We have a very simple function, t times sine of omega t. You can imagine trying to find a Laplace transform with the integral definition will involve several integration by parts. But here we can just say that the Laplace transform of sine of omega t is known to us. It's omega over s squared plus omega squared, and therefore the Laplace transform of f of t is simply going to be minus the derivative of the Laplace transform that we have. Well, that's going to be minus. The top becomes omega times minus 2s divided by s squared plus omega squared squared. Simplifying, we get 2 omega s at the top, and the bottom is s squared plus omega squared squared. Next example is t squared e to the minus 2t. And there are two ways we can do it. We can try to do it with the moments result, which we just had earlier, or we can try it to use the shift theorems and say that we have a Laplace transform of t squared, and e to the minus 2t shifts it by 2. So let's do it both ways. We know that the Laplace transform of e to the minus 2t is 1 over s plus 2. And also the Laplace transform of t squared for the alternative way is 2 factorial over s cubed. So, if we try to do Laplace transform as a moment, then that's going to be the second derivative with a positive sign in front of it, because minus 1 squared is plus 1, of 1 over s plus 2. So this ends up being the derivative, a second derivative of s plus 2 raised to the power negative 1, and so it's a derivative of minus s plus 2 to the negative 2, which ends up being just 2 over s plus 2 cubed. Alternatively, we can use the shift theorems and just say that the Laplace transform of g of t is simply the shift of 2 over s cubed so that ends up being 2 over s plus 2 cubed. With the next function, there's also two ways to do it. We can look at it as a third derivative of the Laplace transform of h of t minus 1, we have derived this in the second lecture. It's e to the minus s over s. Or we can try to use the shift theorems and rewrite this function as a series of shifts of polynomial functions. Alright, so if we try to do the three derivatives of that expression, that's going to be not so easy, but doable. So we're taking minus third derivative of e to the minus s. Let's rewrite it as e to the minus s times s to the negative 1. Well, now we're taking the second derivative of, well, apply the product rule to this. It's going to be e to the minus s times s to the minus 1 minus e to the minus s times s to the negative 2, which can be rewritten as minus the second derivative of e to the minus s multiplied by minus s to the negative 1 minus s to the negative 2. Well, this ends up being minus the first derivative of, again I have to apply the product rule, minus e to the minus s times minus s to the negative 1 minus s to the negative 2 plus e to the minus s multiplied by the derivative of this, which ends up being positive s to the negative 2 plus 2 s to the negative 3. Simplifying this leads to, if I factor out e to the minus s, I get s to the negative 1 only once, I get s to the negative 2 twice, and I get 2 s to the negative 3. Computing the last derivative gets us minus e to the minus s times this whole, I can't even call it a polynomial because it isn't, plus e to the minus s multiplied by, taking the derivative of the inside makes it minus s to the negative 2 minus 4 s to the negative 3 and plus minus 6 s to the negative 4. This simplifies into e to the minus s multiplied by, well, we get minus and minus cancelling out on the first term and minus cancelling out on all of the minuses inside of the second term. So we get s to the negative 1 only once, we get s to the negative 2 1 and 2 times, so it's 3 times. S to the negative 3 is appearing 2 times and 4 times. And s to the negative 4 appears 6 times. Okay, so this is one way of doing that. I'm going to erase the second line and move things a little bit up so that I have space to do it the other way. Alright, the alternative way is to try to use the shift theorems. Well, before we can use the shift theorems, we have to rewrite function u of t as a series of shifts of polynomial function. So we can write t as t minus 1 plus 1. We can always do that, and t was cubed, so we cubed this thing to 2 multiplied by h of t minus 1. Opening it up gives us t minus 1 cubed times h of t minus 1 plus 3 t minus 1 squared times h of t minus 1 plus 3 t minus 1 times h of t minus 1 plus just h of t minus 1. And the Laplace transform is just a series of Laplace transforms of shifted polynomials. The polynomial t cubed has a Laplace transform 3 factorial divided by s to the power 4. And since this function originally was shifted, it has to be multiplied by e to the minus s. The transform of t squared is 2 factorial over s cubed. And again it was shifted, therefore we have to multiply by e to the minus s. The Laplace transform of t is 1 factorial over s squared. And again it is shifted, so it gets the factor e to the minus s. And the last is just the Laplace transform of h of t minus 1, which is e to the minus s over s. And as you can see, this expression matches the expression we obtained previously perfectly. With s to the 4th in the bottom, that becomes s to the negative 4, and 3 factorial is exactly 6, so we get exactly the same coefficient as here. 3 times 2 factorial is 6, so again same coefficient here. 3 times 1 factorial is 3, and just 1. Okay, let's look at the sister theorem to the moments, which is the Laplace transform of the derivatives. And just as before, as we observed with shifting terms, there was a duality to these theorems. There is a duality to the current two theorems. We have the Laplace transform of moments given as derivatives of Laplace transforms. And we start taking the Laplace transform of the derivatives, that will end up with multiplications of the some power. Just as before, we're going to assume that a function that we have, in this case it's y of t, has a Laplace transform, and we're going to call it capital Y of s. Then the Laplace transform of the derivative is going to be the multiplication of the Laplace transform of y by a factor s, but there's a twist. We have to subtract the initial value for y, and that's the initial value for y of t, so we plug in t equals 0 into the original function y right here, and that's the Laplace transform of the derivative. We're going to see in the proof how this y of 0 appears. And on the opposite side of things, if we compute the antiderivative of y, which I'm going to compute a very specific antiderivative, integral from 0 to t of y of tau d tau, that is going to result in a division by s of the Laplace transform. And there will be no initial conditions on that, because the initial condition on this integral when we replace t with 0 is 0. And again, we're going to see in the proof how that plays out. Alright, let's prove it, and this time we're going to prove it directly. So we're going to take a Laplace transform of a derivative. We compute these integrals with the integration by parts, and I'm going to assume that u is e to the minus st, and dv is y prime dt. That makes du to be minus s e to the minus st dt, and v is simply y of t. Well, this integral changes into y of t times e to the minus st, evaluated from 0 to infinity. And again, I'm not going to plug in infinity, I'm going to compute the limit of this product at infinity, plus, because minus and minus make it plus, the integral of y of t times s e to the minus st dt. So the big question is, what is this product when t goes to infinity? The answer to that lies in the fact that y of t does have a Laplace transform. So let's imagine that the product y of t times e to the minus st here converges to something non-zero. Well, that means that this function that we're integrating here is going to be positive for infinite amount of time, and this integral will never converge. But we assume that y of t had a Laplace transform, and therefore this integral has to converge, and therefore y of t times e to the minus st has to converge to 0. So therefore this product at infinity will converge to 0. When I plug in y t equals 0, then e to the minus st becomes 1, and y of t becomes just y of 0. So this becomes minus y of 0 plus s times the integral of y of t times e to the minus st dt, which we recognize as a Laplace transform of y. I'm going to derive one more formula that we're going to use later today, which is the Laplace transform of a second derivative. And the way I do it will help you with the homework. You might imagine I will try to take an integral, but it's a lot easier. I can now use the formula I just derived to derive a new formula for the second derivative, because the second derivative is the derivative of the derivative, and therefore, by the formula I just derived, it's going to be minus y prime of 0 plus s multiplied by the Laplace transform of the derivative. And that is y of 0 with a minus sign plus s times y of s. So that simply becomes minus y prime of 0 minus s times y of 0 minus s squared times capital Y of s. And again, remember that y of 0 and y prime of 0 come from the original function y that defined in the t domain, while y of s is the Laplace transform that defined in terms of s. The last thing that we need to take care of is the Laplace transform of the antiderivative. Well, that's going to be the integral of something with the integral. And we're going to compute this integral again using integration by parts, but this time we're going to assume that u is the integral. Let me move it a little bit down so that that 3 is not in the way. And v is going to be dv is going to be e to the minus st dt. Well, that will make du simply y of t dt, because the derivative, the antiderivative, is the original function. And we'll make v to be minus 1 over s e to the minus st. With this, it changes the integral into the following: minus 1 over s e to the minus st times the integral from 0 to t of y of tau d tau. That has to be evaluated from 0 to infinity. Minus minus makes it plus. And I'm going to factor out 1 over s out of the integral. Get this. The last integral is undoubtedly the Laplace transform of y. So what we need to figure out is what happens with this big product right here when t goes to 0 and t goes to infinity. Well, when t is 0, this integral is 0. So we can just say that this is going to be 0 at 0. At infinity, what happens is this integral might actually diverge, but e to the minus st converges to 0, and quite quickly. And so if we try to apply the L'Hopital's rule, we're going to get a limit of e to the minus st times y of t yet again. And as we said before, since e to the minus st times y of t has to converge to 0, that limit has to be 0 as well. So I'm going to skip the details. I'm just going to say that this evaluates to 0 at both 0 and infinity, and therefore this is just going to be 1 over s times capital Y of s. There are a couple of remarks that I want to make about these terms. First, again, there is duality. Just like in the case of the shift theorems, here multiplying by t in the time domain results in the derivative in the Laplace transform domain. Taking the derivative in the time domain results in multiplications by s in the Laplace transform domain with a little twist. Another remark that I want to make is that I skipped the details on why these things converge to 0 and why this evaluates to 0 at infinity. If you're interested, you can always ask me a question. And just state that the improper integrals for the Laplace transform of y, and Laplace transform of y prime are assumed to be convergent and existing. So let's look how the results we just derived help us solve initial value problems. You may remember from your differential equations class that you can solve this equation with the help of the integrating factor technique and then solve for the constants using your initial condition. With the Laplace transform, it changes slightly. So what we're going to do is we're going to take the Laplace transform of both sides of the equation. That's going to be just a summation of the Laplace transform of the derivative plus the Laplace transform of the function itself. The Laplace transform of the derivative is s times some unknown function y of s. We're just assuming it exists, minus the initial condition, which is 3 in this case, plus y of s. The Laplace transform of the right hand side is going to be the Laplace transform of the exponential function and Laplace transform of the Heaviside function. Again, we can assume that the constant 1 only is 1 for t greater or equal than 0, and so the Laplace transform of this becomes 1 over s plus 1 for the exponential function plus 1 over s for the Heaviside function. And as a result, we have the following equation. That some combination of capital Y of s should be equal to 1 over s plus 1 plus 1 over s, which results in the following equation, that y of s multiplied by s plus 1 should be equal to 1 over s plus 1 plus 1 over s plus 3. And that means that y of s is 1 over s plus 1 squared plus 1 over s times s plus 1 plus 3 over s plus 1. Okay, the transform problem led to a solution that is Laplace transform of something. So what we have to do is we have to figure out what function might have this as the Laplace transform. So we need the inverse Laplace transforms of these functions. So what could be a function that leads to the Laplace transform that looks like 1 over s plus 1 squared? Well, it seems like that s plus 1 is a shift, which means that the original function was multiplied by e to the minus t. But we still need the inverse Laplace transform of 1 over s squared. Well, we know what function has this as Laplace transform. It's just a function t. So this is just e to the minus t times t. Also, it's very easy to compute the inverse Laplace transform of 3 over s plus 1. That is simply 3e to the minus t. The last one is a little bit trickier. Because we've never seen a function that has a Laplace transform of this form. Well, if you remember from calculus, when you're integrating fractions like that, you broke them into simpler fractions. And that's what we're going to do. We can assume that 1 over s times s plus 1 can be broken into two fractions, a over s plus b over s plus 1, which leads to the equation that 1 equals a times s plus 1 plus b times s. Setting s equals 0 will lead to a being 1, and setting s equals negative 1 will lead to b equal negative 1. And as a result, the Laplace transform, the inverse Laplace transform of 1 over s times s plus 1 equals the inverse Laplace transform of 1 over s minus 1 over s plus 1. And the Laplace transform of 1 over s is simply the Heaviside function. And 1 over s plus 1 is e to the minus t. If we combine these results, we will get that the inverse Laplace transform of capital Y of s equals e to the minus t times t plus 3 e to the minus t plus the heaviside function minus e to the minus t. So that simply can be rewritten as t e to the minus t plus 2 e to the minus t plus 1 for t greater or equal than 0. Let's look at some second order equations. We have to transform the right hand side. And that's going to be s squared y of s minus s times the initial condition at 0 minus the initial value for the derivative plus 3 times s times the Laplace transform of y minus the initial condition for y at 0 plus 2 of y of s. This can be simplified into y of s is multiplied by s squared 3s is 2, and the values that we subtract are plus s minus 4 plus 3. So it ends up being simply minus 1. On the other side we have Laplace transform of 0, which is just 0. Therefore the equation that we have reads the following: y of s times s squared plus 3s plus 2 plus s minus 1 equals 0. As a result, y of s must be 1 minus s divided by s squared plus 3s plus 2. And this looks like a complicated function to take the inverse Laplace transform of. But again, we can try to break it into simpler fractions. The denominator factors into s plus 2 times s plus 1. So therefore it can be rewritten as a over s plus 2 plus b over s plus 1. This leads to the equation that 1 minus s must be a times s plus 1 plus b times s plus 2. And if I plug in s equals -1, then I will get that 2 equals a times 0 plus b times 1. If I plug in s equals -2, I will get 3 equals a times -1 plus b times 0. And as a result, y of s must be -3 over s plus 2 plus 2 over s plus 1. Computing the inverse Laplace transform gives us inverse Laplace transform of -3 over s plus 2 plus inverse Laplace transform of 2 over s plus 1, and this gives us -3 e to the minus 2t plus 2 e to the minus t. Another example is a non-homogeneous equation, and you solved it in the differential equations classes with either method of undetermined coefficient or variation of parameters of some sort. So let's see how we can do it with a Laplace transform. Y double prime turns into s squared times y of s minus s times the initial condition for y, which is 1, minus the initial condition for the derivative. Y prime changes into s times the Laplace transform of y minus 1, and y just has a Laplace transform y of s. We can simplify this into y of s multiplied by s squared minus 2s plus 1. And this equation has double roots, s minus 1 squared, and the roots of the characteristic equation would be 1 and 1. So we're going to see e to the t and t e to the t in our solutions. The other terms add up to minus s, and we have plus 1 and plus 2. The Laplace transform of 3 is simply 3 over s. Therefore, the transformed equation turns into which gives us the function y of s equal s minus 3 plus 3 over s over s squared minus 2s plus 1. We can move the s in the denominator and write s squared minus 2s plus 1 as s minus 1 squared, and the numerator becomes s squared minus 3s plus 3. If we try to use the partial fraction decomposition for it, then the partial fractions should be something like a over s plus b over s minus 1 plus c over s minus 1 squared. This leads to the following equation, that s squared minus 3s plus 3 should be a times s minus 1 squared plus b times s minus 1 plus c times s. Plugging in s equals 0 will give us the value of a. So a should be 3. Plugging in s equals 1 will give us 1 equals a cancels out, b cancels out, c. So we find that c is equal to 1 and a equals to 3. And the last thing is to find b. And we can find b by plugging in something easy into s. So if we plug in s equals 2, then this will result in the equation 4 minus 6 plus 3, so it's going to be 1 equals a times 1 squared, so just a, b times 2 plus 2c. And since we already know A and C, we get that A is 3, C is 1, and B has to be -2. Therefore, function y of t is the inverse Laplace transform of this partial fraction decomposition. We get 3 over s, we get -2 over s minus 1, and we get 1 over s minus 1 squared. 3 over s gives us just 3 h of t minus 2. S minus 1 is just e to the t, and s minus 1 squared is, we can look at it from two different perspectives. We can look at it as a shift of the function 1 over s squared, which was the Laplace transform of t, and so if it's a shift it has to be multiplied by e to the t. Or we can look at it as a derivative of the term 1 over s minus 1, and the derivative in the Laplace transform means multiplication by t in the time domain. So regardless how we look at it, it's going to be the same function that has this Laplace transform, t e to the t. And if t is greater or equal than 0, this turns into simply 3 minus 2 e to the t plus t e to the t. The last example that I want to consider is something that would not be very convenient to solve with the methods of differential equations, since the function that's on the right, f of t, is discontinuous, and we treat discontinuous functions as sort of a differential equation stops, changes, then continues from where it stopped with a new right hand side, then stops again, changes again, and etc., etc. Just to illustrate how lengthy and cumbersome the process is, I'm going to solve it with the methods that you learn in your differential equations classes. So this is simple first order differential equation, and we have to break the solution process into 3 domains. So the first, we're only going to consider domain t is going from 0 to 1. For this domain, the equation form, and the initial condition is y of 0 equals 0. If we solve with the method of integrating factor, then the integrating factor here is mu of t equals e to the 2t, and as a result, y times e to the 2t should be the integral of 0 times e to the 2t dt. And that means that y should be just a constant times e to the minus 2t. Well, since y of 0 equals 0, it leads to y of t being 0 all the time, but again, only for t being in the interval 0 to 1. The second interval, t belongs to 1 to 2, the equation changes, becomes y prime plus 2y equals 1. And the initial condition now is y of 1 equals 0, because previously the function was always 0. Solving that with the same integrating factor leads to y times e to the 2t should be the integral of e to the 2t times 1 dt. So that means that y times e to the 2t should be constant plus 1/2 e to the 2t. Simplifying this leads to y being equal c times e to the minus 2t plus 1/2. Since y of 0 equals 0, since y of 1 equals 0, we get that 0 should be the same as c times e to the minus 2 times 1 plus 1/2. As a result, c equals minus 1/2 times e to the 2. Therefore, the solution y of t is simply minus 1/2 e to the 2 minus 2t plus 1/2. The last time interval that we have to consider is t belonging to 2 to infinity. This one is a little bit more complicated. We have the differential equation y prime plus 2y equals 0 this time, but the initial condition is not that easy to obtain, so y of 2 has to be whatever the previous formula stopped at. We assume that the solution to the differential equation is continuous, and therefore y of 2 should be the same as what the previous expression was approaching as t was approaching 2. So it's minus 1/2 e to the 2 minus 2 times 2 plus 1/2. So it is 1/2 times 1 minus e to the negative 2. Again, solving it with the same integrating factor, because the integrating factor didn't change, we get that y should be just constant times e to the negative 2t, and since we have we get the following expression. We get that 1/2 times 1 minus e to the negative 2 should be the same as c times e to the negative 4. Therefore, constant is simply 1/2, and we multiply everything by e to the 4 of e to the 4 minus e to the 2. And the final expression for y of t is simply 1/2 e to the 4 minus e to the 2 times e to the minus 2t. When we summarize everything, then we get that y of t was 0 for t being from 0 to 1. Then y of t shifted to minus 1/2 e to the 2 minus 2t plus 1/2 for t in the interval from 1 to 2. And then finally, it's 1/2 e to the 4 minus e to the 2 times e to the minus 2t, when t belongs to the interval from 2 to infinity. This process is quite complicated. We can use an alternative form of the variation of parameters formula that says the following, that y of t is the initial value times e to the minus 2t plus e to the 2t negative 2t integral from 0 to t of e to the 2 tau f of tau d tau. Since the initial condition is 0, we get that the function y of t is just a part with the integral. And function f of t behaves differently when tau is from 0 to 1, when tau is from 1 to 2, and when tau is from 2 to infinity. So we have to break this solution again into 3 time intervals. For t in the interval from 0 to 1, we get that y of t is just e to the minus 2t times the integral of 0. So it's always 0. For t in the interval from 1 to 2, we get that y of t will be the e to the minus 2t times the integral. Well, since f of tau is only going to be non-zero from 1, then we get that it's the integral from 1 to t of 1 times e to the 2 tau d tau. So it's e to the minus 2t times the antiderivative, which is 1/2 e to the 2 tau evaluated from 1 to t. So we get e to the minus 2t multiplied by 1/2 e to the 2t minus 1/2 e to the 2. So when we multiply by e to the minus 2t through, we get that this is going to be 1/2 minus 1/2 e to the 2 minus 2t. And that's exactly the same as the solution we obtained before. For the time interval from 2 to infinity, the integration is only going to be performed from 1 to 2. So we get y of t is e to the minus 2t times the integral from 1 to 2 of e to the 2 tau d tau. And that is e to the minus 2t times 1/2 e to the 2 tau evaluated from 1 to 2. So that is e to the minus 2t times 1/2 of e to the 4 minus 1/2 of e to the 2. And again, it's exactly the same as the solution we obtained before. And I wouldn't say that this process is any easier than the process that we had to go through before. Lastly, I would like to try to solve this with Laplace transforms. The Laplace transform of the left-hand side is going to be s times y of s minus y of 0 plus 2 y of s. And that means the y of s is simply multiplied by s plus 2. And since the initial condition was 0, that's going to be it for the Laplace transform of the left-hand side. For the right-hand side, we have the Laplace transform of f of t, which is the function that turns on at 1 and turns off at 2. That means that we're taking the Laplace transform of h of t minus 1, which turns on at 1, minus h at t minus 2, which is going to turn everything off at 2. And the Laplace transforms of those, we have computed them before, so it's just going to be e to the minus s over s minus e to the minus 2s over s. And as a result, we have an equation that y of s multiplied by s plus 2 should be the same as e to the minus s over s minus e to the minus 2s over s, which leads to the function y having the following Laplace transform. It's e to the minus s over s times s plus 2 minus e to the minus 2s over s times s plus 2. To find the inverse Laplace transform, I would like to break down the fraction 1 over s times s plus 2 into simpler fractions, a over s plus b over s plus 2. Easy to see that a has to be 1/2 and b has to be negative 1/2. And as a result, y of s can be written as equals e to the minus s times 1/2 over s minus 1/2 over s plus 2 minus e to the minus 2s times the same thing. The inverse Laplace transform is now easy to find with the shifting theorem. Let's find the inverse Laplace transform of 1/2 over s minus 1/2 over s plus 2. That is equal to 1/2 of h of t minus 1/2 of h of t times e to the minus 2t. The reason I put Heaviside function on both of the terms because I know that later on e to the minus s and e to the minus 2s will lead to shifts, and so I'm going to simplify it so that performing those shifts will be easier. As a result, the inverse Laplace transform of y of s is just the sum of these two functions shifted. So at first I have this function shifted by 1, so every t is going to be replaced with t minus 1, and the second term will give me this function shifted by 2. As you can see, the solution with the Laplace transform didn't require us to look at the different time intervals. It did it all together for all t, and that's a convenience of the Laplace transform. It just does it for us. The last thing I want to do today is to compute all of the examples we looked at today with the help of Mathematica. The first example was the Laplace transform of the moment of the sine, so it's t times sine, and notice that I use the space between t and sine. If you don't use it, then it's going to be a single variable t sine, and the Laplace transform will not know what to do with it. So again, don't forget about your spaces. And it was omega t inside. Again, I used the space in terms of t, and I want the output in terms of s. If you compare it to the output we've got in the notes, it's exactly the same. We also computed the Laplace transform of t squared times e to the negative 2t. And that's exactly the same answer as we got in the notes. The last thing we computed was the function t cubed times the Heaviside function t minus 1. And this answer looks a little bit strange, but after a quick inspection we can see that the expression we got in the notes and the expression that Mathematica gave us are absolutely equivalent. The second half of the lecture was dedicated to solving initial value problems, and I want to do it two ways. I want to do it with methods of differential equations and the Laplace transform. Mathematica has a differential equation solver, and that's a command dsolve that will do this for us. And the equation, the first equation that we considered, was y prime, and it has to be y prime of t plus y of t, and that's equal to, and notice I use double equal sign because the double equal sign is the comparison operator. Single equal sign is the assignment operator, and if you don't use the double equal sign, dsolve will complain or something will happen that will prevent you from solving your differential equations correctly. So that was equal to e of minus t plus 1. And we want the solution as a function y of t, and the whole equation is given to us in terms of t. And the Mathematica will give us the general solution with the constant here. We had the initial value, so we should be able to figure out what this constant is, and dsolve can do that for us. But in order for dsolve to know that there is an initial condition, we have to give it to it as a second equation. Dsolve can solve sets of equations at the same time, and the initial conditions are given as second or third equation in the first argument. Notice I'm using curly braces. That means that I want to group these equations as a first argument. And again, use double equal sign, and initially y is 3. If I evaluate, I get the answer that is exactly the same as the answer we got in the notes. So what happens if I don't use a double equal sign? Well, Mathematica doesn't know what to do. Restoring double equal sign here makes everything alright. However, if I forget to use the double equal sign when I specify the initial condition, then you notice that something happened here. I don't have the second equation anymore, I have just 3. If I restore the double equal sign, this doesn't help. All of a sudden this doesn't work anymore. What happens now, if you notice that y is now having black color, that means that y is a known symbol to Mathematica. And Mathematica remembers now that y at 0 has to be 3. So what we have to do is we have to clear any values that are assigned to the symbol y. Once we do it, we can see that y turned blue, and now dsolve works as expected again. So make sure you use your double equal signs. Make sure you specify that y is a function of t, because if you forget to do that, Mathematica doesn't know what to do again, and so it won't solve your equation. Sometimes it will complain, sometimes it just fails. So if something like that happens to you, it means that somewhere you just didn't give Mathematica the right information. Alright, let's use the Laplace transform. And Laplace transform can actually take in the whole equation. If I just copy the equation into the Laplace transform, and it will compute the Laplace transform for us. Notice that it doesn't know what the Laplace transform of y is, so it just says, here is the Laplace transform of y. And we're going to replace it with y of s. And do the same here. And y of 0, we know that's 3. Now we need to solve for y of s. This Laplace transform looks a little bit unfamiliar because we didn't do the grouping of the terms and Mathematica did it for us. So let's see what kind of simple fractions this big fraction can be broken into. Mathematica has an apart command that does a partial fraction decomposition. And it looks a little bit different as well. Well, that's only because we didn't do the grouping of the terms. We did the partial fraction decomposition only of the second term, and the second term had the fraction 1 over s plus 1 in it. So we did a little bit of double counting, and if I do the inverse Laplace transform of this, then you can see that the expression that I get from the inverse Laplace transform is exactly the same as the expression I got with the dsolve command. I'd like to skip the second example because the second example was a simple homogeneous second order equation, and I would rather do the third example, which was a second order non-homogeneous equation, and I think it will be a little bit more interesting. And again, let's use the dsolve command first. And the equation was y double prime of t minus 2y prime of t plus y of t was equal to 3. Again, use your double equal sign. The initial conditions were, and in order to specify initial conditions, I need to use curly braces to tell dsolve that I have a set of equations. Y of 0, double equal sign, 1, y prime of 0, double equal sign, minus 1. We need the function y of t, and it's a function of t. And the solution is exactly the same as we have obtained in the notes. Let's use the Laplace transform now. If I transform the equation, then again Laplace transform doesn't know what the function y is, so it just says the Laplace transform of y, which I'm going to replace with y of s. And now I have to replace y of 0 with 1 and y prime of 0 with -1. Now I need to solve for y of s. Computing the partial fraction decomposition gives us coefficients 1, -2, and 3, and that's exactly the coefficients we have in our notes. And the inverse Laplace transform. And it doesn't really matter if I plug in the partial fraction decomposition or the original big fraction. Mathematica can do it either way. And the answer is exactly the same as the one we have obtained with the differential equation solver command. The last example we considered was the example of the piecewise defined function f of t. And let me define the function f of t. The Mathematica has a special language to defining functions. So I'm saying that here they have a function f of t, and the underscore is used in Mathematica to tell Mathematica that this is going to be the parameter. And I'm using colon and equal to say that, well, what follows is the definition of the function f of t. And inside that definition I will have to use t, not the t underscore. The mathematical language has its quirks, but it's a convenient one to use. So f of t was a piecewise defined function, and Mathematica has a command for piecewise defined functions. And what it needs a list of lists. In this list you specify the values and the condition where those values hold. The first one was when t was between 0 and 1. The second one was value 1 for t between 1 and 2. And the last one was 0 again for t greater than 2. That defines the function f of t. Let's plot it just to make sure. That the function does exactly what we want it to do. And you may be wondering, is there a difference between defining functions as piecewise functions or as a summation of Heaviside functions? So I'm going to define a new function g of t that does exactly the same thing as the f of t, just to compare what's going to be different if we use g of t or f of t. So now g of t is a function that looks exactly the same as f. So what happens when we use the desolve command? The equation was y prime of t plus 2y of t, and that equals to f of t. The initial value was y of 0 double equals 0. We need the function y of t in terms of t. When we evaluate, we get a piecewise defined function. And what I want to do, I want to plot it. So I'm just going to copy and paste. I'm going to plot it in terms of t from 0 to 5. And this is what happens. So the function was 0 up to 1. Then when we turned the switch on, the function started growing and when we turn the switch off, the function went back to 0. Let's see if I do the same thing by the function g of t. Well, the answer looks a little bit different. The answer has the unit step functions and other things. But the result is exactly the same. If you plot it, you get the same function. What happens if you take the Laplace transform of f of t? And the Laplace transform of g of t? Will they be different? They can be different. And they're not. They're absolutely equivalent. So if we try to solve the differential equation with the Laplace transform, it doesn't really matter if you give it a piecewise function or if you give it a combination of Heaviside functions. And I would say it's a cleaner approach if we use the Heaviside functions. So I'm going to do the same thing as I did before. Replace the Laplace transforms with y of s and solve for y of s. There's a typo. Oh, y of 0 was 0. Okay. So this is the Laplace transform of y of s. And what we did is we computed the partial fraction decomposition of this term. But the part command doesn't work very well when we have exponential terms in there. So what I'd rather do is I would take them outside. And now the part command gives us the same partial fraction decomposition as we have obtained in the notes. It's 1/2 and minus 1/2 as the coefficients for the fractions 1 over s and 1 over s plus 2. Nevertheless, if I do the inverse Laplace transform, then I get an expression that looks like the expression we had before. And if I plot it, get a function that looks exactly like the functions we obtained before. So what we have seen today is that Mathematica has two very powerful frameworks, the differential equation solver and the Laplace transform framework that can help us with the differential equations. And we see that both methods give us exactly the same answers. And although it is really not different in terms of how much work you need to do to solve the equations with the dsolve command or the Laplace transform command, I want to point out that the Laplace transform is useful for different reasons. It's useful for analysis of the equations because, what we're going to see later, it introduces the framework of system transfer functions, and those frameworks are crucial. And those system transfer functions make the analysis very easy in applications like control systems and electrical circuit analysis. Not to mention the thing that the Laplace transform is crucial in analysis of partial differential equations. Well, this concludes our lecture today. Thank you for listening, and I'll see you in the next video.